Hello everybody. Today's lecture is about Bell's experiment. This experiment was designed by the physicist John Bell in the 1960s. And this experiment has provided deep insights into the nature of quantum mechanics, into the nature of entanglement. And even today, it's a topic of active research in quantum cryptography, quantum information, quantum computation. Okay, so let's start with a philosophical question. Can we experimentally test whether we live in a quantum world? What do we mean by this? Well, all the quantum weirdness, the fact that measurement outcomes are probabilistic, that just looking at the system changes its state, the fact that particles do not have trajectories and instead they are in this weird kind of superposition where they take all possible paths simultaneously with some amplitude. Is all this an intrinsic property of nature, or does it reflect the fact that we only have an incomplete picture, that quantum mechanics is an incomplete theory? That is, if we knew more about the mechanism behind the scenes, if we knew more about the gears and pulleys that are acting behind the scenes, would it actually look much more natural? This is what Einstein believed. Okay, so the kind of mechanism that Einstein was looking for that acts behind the scenes was a local and deterministic mechanism. By local, what that means is that there's no action at a distance. Of course, local also means that there's no faster than light communication. The theory of relativity holds. And deterministic, meaning that there are no such probabilistic outcomes to measurements, that the system actually has definite values for physical quantities like momentum, or speed, or spin, etc., or bit or sign, etc. I'm sure you've heard the quote, Einstein's quote, "God does not play dice with the universe." Okay, so this is what we are looking for, and in the previous videos we talked about the EPI experiment, the Einstein-Podolsky-Rosen thought experiment, which was designed to precisely think about these issues. Now, in the 1960s, in 1964, John Bell designed a remarkable experiment. This was an honest-to-goodness experiment, not just a thought experiment. And it was an experiment which had one of two outcomes. So if you do this experiment and the outcome is outcome one, we'll see what all these outcomes mean later, but if the first outcome happened, then you could conclude that nature is inconsistent with quantum mechanics. That quantum mechanics is false, but that nature can be explained by some kind of local hidden variable theory. It's consistent with some local hidden variable theory. On the other hand, if the second outcome holds, then this would imply that nature is consistent with quantum mechanics, but it's inconsistent with any local hidden variable theory. Meaning that if the second outcome were true, then the kind of theory that Einstein had spent the last 20 years of his life searching for could not possibly hold. It would have been experimentally proved that, in fact, all such theories are ruled out by the way nature behaves, can be observed to behave. Now, the Bell experiment relies on sophisticated properties of entangled qubits, actually of the Bell state. And the Bell experiment has been performed numerous times, and the results have always been consistent with quantum mechanics and inconsistent with local hidden variable theories. So always it's outcome 2 within experimental error that's held. Okay, let's look at Bell's experimental setup. So Bell assumed that the apparatus for this experiment is divided into 2 parts, which are far enough apart that during the course of the experiment, light does not have enough time to travel from one to the other. So the 2 pieces are completely isolated from each other. Of course, this can be achieved by making the duration of the experiment so short that you could actually have these 2 parts of the apparatus at 2 ends of your lab. Okay, so now for our purposes, let's think of these 2 parts of the apparatus as 2 boxes. The first box gets as input one of 2 bit values, 0 or 1, which we'll call X. And the second box gets as input a bit, which we'll call Y. What the boxes are supposed to do is they're supposed to output also a bit, 0 or 1. And what they're trying to do is, if both the input bits X and Y are 1, then the output bits A and B are required to be different from each other. So they could be either 0, 1 or 1, 0. In all the other 3 cases, we want the outputs of the 2 boxes to be the same, either 0, 0 or 1, 1. Now what Bell was able to show is that if the physics of the boxes is described by local hidden variable theory, then they cannot succeed in this task with probability exceeding 3/4 or 0.75. So no matter what the physics of these boxes is, no matter what the physical theory is, as long as it's a local hidden variable theory, the chance of success is at most 3/4. On the other hand, he was able to show that if the 2 boxes share a Bell state, meaning that there's 1 qubit in the first box and a qubit in the second box, so that these 2 qubits are entangled and they form this Bell state 0, 0 plus 1, 1, then there are certain measurements that you can make on these 2 qubits, that the 2 qubits can make, in such a way that they succeed in this task with probability as high as 0.85. And so if you perform such an experiment, if you actually realize this experiment, and if within your error tolerances you show that your success probability in this task is strictly greater than 0.75, then you would have shown that nature is inconsistent with any local hidden variable theory, and it's consistent with quantum mechanics. Well, actually, to show that it's consistent with quantum mechanics, you'd have to show that your success probability to within your error tolerances is really 0.85. Okay, so let's now see why a local hidden variable theory does not allow you to succeed in this task with probability greater than 3/4. So the fact that it's a local hidden variable theory and the fact that these 2 boxes cannot communicate with each other, what this implies is that the output of the first box can depend on X, but it cannot depend on Y, the input to the second box. And similarly, the output of the second box cannot depend upon X, the input of the first box. Also, the fact that we want to show that the success probability cannot be greater than 3/4. For contradiction, let's assume that the success probability is greater than 3/4. Well, in this case, the boxes cannot afford to be incorrect on any of the 4 possible inputs, 0, 0, 0, 1, etc., etc. Okay, so now suppose So what this means is that if the input was x equal to 0 and y equal to 0, then the two output bits must be the same. A must be equal to B. So let's assume without loss of generality that A equal to B equal to 0 in this case. Now by locality, if we were to switch only one of the inputs, let's say y, and switch y, make y equal to 1 while leaving x equal to 0. So now the first box will still output A equal to 0. But since the two boxes must output the same value on this particular input, x equal to 0, y equal to 1, so in fact, the second box must also output B equal to 0. We can use the same reasoning if instead we leave the input y equal to 0 and now switch x equal to 1. So we now reason that, well, of course, B still must be 0. But now since A must be equal to B, in fact, in this case also A must be equal to B equal to 0. Okay, now let's argue that this further implies that when we give the two boxes the inputs x equal to 1, y equal to 1, they still must output A equal to 0 and B equal to 0. But this is a contradiction because in this case, they were supposed to output different bits. So they were supposed to output either A equal to 0 and B equal to 1, or A equal to 1 and B equal to 0. So that's a contradiction. So let's see how this last step works. This is a little subtle. Okay, so you see, in the case x equal to 0, y equal to 1, the outputs were the first box output 0 and the second box output 0. Well, so let's pay attention to the second box in this case. Well, from the second box's point of view, it was getting as input y equal to 1. It doesn't know whether the first box got input x equal to 0 or x equal to 1. So it must give the same output regardless of which input the first box got. But in the case that the first box got input 0, the second box output B equal to 0. So it must still output B equal to 0 in the case that x equal to y equal to 1. Symmetrically, we can also argue that from the first box's point of view, when it was given input 1, it must output A equal to 0. Because it doesn't know whether it's in the case x equal to 1 and y equal to 0, or whether it's in the case x equal to 1, y equal to 1. So we have argued that in the case x equal to y equal to 1, both boxes must still output 0. And so they are both outputting the same bit, which is a contradiction. Okay, so we've proved our first assertion here that if the boxes are described by local hidden variables, they succeed with probability at most 3/4. This second assertion that if the boxes actually follow quantum mechanics, if they are allowed to share a Bell state, then they can succeed with probability as high as 0.85. This is actually somewhat more involved. And to do this, we need to understand some properties of Bell states, which we'll do in the next video.